Hello and welcome to the ninth tutorial of this course, Reinforcement Learning, offered by NPTEL. I am Abhikar, a PhD student at Indian Institute of Science. So today we'll discuss the following topics. We will first we'll discuss policy gradient algorithm. And if time permits, then we'll discuss a factor protein. Also, there is some backlog which is basically nonlinear function approximation. Approximation uh, for TD learning. Okay, let us revisit the policy gradient algorithm for and also activity algorithm for multi-arm bandit. PG for multi-arm bandit. So there, first thing we have looked at is the set of policies are parameterized. That is all policy we implement in this uh, algorithm will be of the form pi theta, where theta belongs to some parameter space, capital theta. And it's not necessary, but we have considered this this policies are randomized. That means AT is sampled from the distribution by ST parameterized by theta. And how did we update the policies? So ultimate goal is to maximize expectation over pi theta. Mu A. What is that? Is sum over all actions pi theta Several states. Sorry, why I am bringing the stating map? Uh, sorry. So pi theta is performance. Pi theta itself is a distribution over action space. Sum over all actions. Pi theta will mean over overall policies, but this algorithm only talks about policy that can be parameterized by theta. So overall, theta belongs to the set. Now we are considering this parameter space is unbounded. So you can apply uh, gradient descent once the theta update rule for gradient descent. Sorry, gradient ascent, because here we are looking at maximization problem. Have I written ascent scaling correct?
Yeah.
Okay. Theta t is, so this will be plus because ascent, some alpha t, which is the step size, gradient of this quantity. So policy gradient does not keep estimate of or maintain. Of so what does it do then? So this is gradient descent. We cannot. So here mention that we don't know mu a. Theta t plus 1 in case of policy gradient. RT, which is the reward obtained at time t. Gradient of I3 time 80. But this is not very uh, efficient. As you can see, you are neglecting all the past samples. So PhD and okay. So this algorithm is not called factor critic, but the idea from here will be same for pattern. So calculating is uses estimates of.
I think you forgot the baseline, which is
Yes,
the
yes. So
critic. Actor, right? No, no, that is a critic here.
yeah, so yeah, baseline I have not written, but probably for the next equation I like. Um,
Okay, okay, because that turns into a critic, right? That baseline.
no,
The
so
idea of having the baseline converts it to a value function which becomes a critic. No?
so okay, we'll discuss this later. I think uh, so for RL context, it might be, but here I'm not sure. Okay, so estimates of mean rate and theta t plus one is updated as. So yeah, this is the idea. And for RL setup, the goal is to maximize policy development. V by theta. Okay, so let us denote this V by. Let us introduce a new notation that will make my work easier. So sort of overloading of notation. V by rho is expectation. V by theta S, where S is sampled according to the distribution. They are also given a start state distribution. Well, uh, so you want to maximize this and you want to update the uh, theta. So here also your update rule should be something like update rule theta t plus 1 equals to theta t plus gradient of this object. So we'll discuss three expressions of this uh, thing. So this gradient we have to evaluate, right? So before introducing the first expression, let us denote a trajectory by tau. So trajectory denoted by tau, which is nothing but the triplets state, action, and reward. S naught, A naught, R naught, S1, A1, R1, S2, so on. And let P pi rho denote the probability with distribution. Distribution on the this on the set of trajectory. So set of trajectories. So yeah, and also we denote the reward obtained from a trajectory by capital R tau. Capital R tau is the reward obtained from the trajectory. I mean, so we are talking about discounted rewards. So it will mean that equals to 0 to infinity uh, gamma raised to t RT.
What was rho over here?
So rho is a initial state distribution.
Rho.
If you see this equation,
Acha, state you have sampled from rho. Okay, okay.
S0 is having distribution.
Okay, okay.
Okay, so let us now begin with the first expression of the policy gradient, that is delta theta v pi theta. So this is equals to expectation over trajectories from this distribution of trajectory is p pi theta. So what is the expression? Expectation of r tau sum over t equals to 0 to infinity delta theta log pi theta. Okay, so the mistake I was doing is I was right earlier in map setup. I was writing this pi theta as function of uh, is. So that will be true here. So pi theta 80 given st. So you could have written comma, but so this is conditional on state. So you can write given. Okay, so this is called policy gradient theorem, and we'll prove this. So V pi theta rho. Do you agree that this is equals to expectation over trajectories r dot? Is it true? Uh, Anyone has any confusion in this? Okay, as you know, the gradient of this object. So this thing you can also write as assuming that there are only finite trajectories somehow. It's not, but for the sake of simplification of the consequent discussion, let us assume that. So sum over tau, which also could be integration and then uh, okay, we can write in terms of integration. That's fine. Or tau d d by. There will be something will happen which are sort of cryptic. So now assuming that we can interchange derivative and uh, integration, so which is that's why I was trying to write is a summation. Assuming this, so I think I should write it in terms of summation, otherwise it will be very complicated. Sum over tau. So R tau is not a function of theta. Now, this you have seen earlier that we earlier had such expression, some expression, and we handled it somehow in the analysis of activity or reinforce of bandit or multi-bandit. So this we have written as delta theta log of p by theta. And again, the way we have written this equation is
So that term, summation over tau, R tau, and the probability of tau, is basically the return of any trajectory multiplied by probability of seeing that trajectory under policy theta.
yes, yes,
And
exactly.
you're summing over all such trajectories.
Yes, we are taking this expression over trajectories. So now see that this is equals to expectation of over this tau in p phi theta summation. Summation will be that r tau delta theta log p phi theta. So we have something very similar, but this gradient expression is not the same, right? So there is some summation over some pi theta and all, and here you don't have this. So let us, if I write this uh, p pi theta rho, then you will see that I mean things will be fall in place and we'll get this equation. So what is p pi theta rho? Tau. So we are assuming tau is S0, A0, R0, S1, A1, R1, and so on. So what is the probability of seeing tau? So first, what is the probability of seeing rho S0? That is rho of S0. Then given S0, what is the probability that we see action A0? So that is phi theta A0 given S0. Now, given these two things, what is the probability that we'll obtain reward R 0? So for the time being, say just a second, right? We will clean this. Okay, so yeah, we can. I don't know. So reward where R is not a distribution here. Okay, for the let's say there is some distribution, or should I write? Let's write dr. So dr of st 8. So distribution of d1 st8, and the mean of this distribution is basically r of st8. Like we could have also think it as deterministic, but okay, this is also fine. Then multiply it with okay, so then we have to see the next state distribution. What is the next state distribution? P of S 1. I forgot how we are writing the transition probability. Are we writing P of S0 is
I don't think there is any necessity of that DRST80. Yeah, that I think P of S1 given S0 A0, right? And then you have that pi again, and you keep repeating that. Just the first term is that rho S0. Otherwise, you will have this P S1 given. There is no
no,
need for the distribution S0 A0.
no,
Because
what
you
I
have this, you have some probability of S0, then you take an action A0 based on your pi. Then you are transition to S1 with some probability, right? And that is that probability, right? P of S1 given S0 A0. Then you again have what action you will take in S1, which is P of pi of A1 given S1. And that
no,
continues,
so
right?
why I'm writing dr S0 is 0? I agree that that will ultimately will not affect the end result. But why I'm writing is the trajectory also includes the reward, right? S0, S0, R0. So R0. So given S0 and A0, there is some probability that we will get R0, right?
True, but that probability itself has nothing to do with reward, right? That could be anything. It just gets summed over, no? So even if the reward is stochastic, it will get summed over, like marginalized. So what you care about in your P is probably just the transition probability.
No, I couldn't understand your logic. Can I
So
please
what
repeat?
I'm saying is what your P represents over here, P of tau,
Yes, sir.
there is no need to put R, right? Well, R is kind of marginalized, even if it is whether it is deterministic or stochastic. If it is stochastic, it will be marginalized in this equation. So there is no reason to have R.
Yeah.
About
So
this sort of.
P will also be not be affecting. But what do you mean by marginalized? That I couldn't understand.
Meaning what I'm saying is this R is, let's say R is deterministic, right? Then in that case there will be no R, right? It will be just one, right?
Yes,
If R is,
yes,
and even if
right.
it is stochastic, it is the marginal over all R this P represents. So you don't really have to include R in this particular multiplication. Like basically you're using some Markov property, no, over here, and going over like from one state to the other, you're going the trajectory. So this P doesn't have has nothing to do with the R actually. It gets marginalized out. It is for all R, is what I was trying to say. So when you're transitioning to S1 from S0 A0, no matter what the R, it will get summed over, like marginalized in this particular expression. So it is for all the R, doesn't matter. So R doesn't really figure in this equation, is what I was saying.
No, I couldn't understand actually, but R is will not affect this equation. The reason I understand is different. That is not function of theta. That's why it will not affect it. But
So see, so whether you get a reward or not, right? Under policy, well, will be a policy. So you keep taking actions according to your policy. R doesn't figure anywhere in this equation, no, the probability. It doesn't matter. The transitions will happen irrespective.
yeah, but tau is tau is S0, A0, R0, S1, A1, R1. So probability of this is also counted in this, right?
Okay.
Probability of
So I was
seeing
just
R.
thinking, I was just thinking, no matter what the R0, like even if it is stochastic or deterministic, it will be just a sum over all R zeros or sum over all R ones, and the terms in this expression would just be multiplication without the R, is what I was thinking. But maybe I'm wrong. Doesn't matter. You continue. Maybe I'm saying something wrong.
Yeah, some constant will be multiplied. But yeah, I'm also saying that it will not be changing the ultimate result, and uh, the reason because that doesn't depend on theta. Okay, I'm not writing R. Uh, say we from the trajectory we are eliminating R. Fine. So uh, then given S1, we have to multiply this. What is the probability of taking action A1 given S1? Then P S1 A1 S2 and so on. Now, what we are interested in is log of this quantity. So log of multiplication will become summation and we'll have sum over all these things. So here will be log of rho is 0 plus, let us write this uh, log of policies. So all the expression which are coming from policies, let us write separately, AT given ST. And then let us write the transition probabilities equals to 0 to infinity log of P uh, is T A T S T plus 1. Now, when we'll take, so now if we have taken this reward, then there will be another summation of log of dr R0 given S0 A0, right? Sorry, RT given ST AT for t equals to 0 to infinity. Now, that doesn't depend on uh, theta. So, these two quantities. These two quantities doesn't depend on theta. So when I'm taking gradient with respect to theta, then those things will be 0. The terms corresponding to those two terms. So delta theta summation equals to 0 to infinity log of pi theta AT given ST. So this when replaced in this equation. So finally, we delta on delta theta V pi theta rho is expectation of trajectories. The distribution is d pi theta rho. R tau delta theta sum over t equals to 0 to infinity of pi theta. Now we have this till we have this as expectation. So when if you consider gradient descent, then we can just write this expression in this equation, and we'll get the gradient descent algorithm. But we do not know how to compute this expectation. So, but we do is collect TX trajectory. Okay, T is something else here. So let's write IF trajectory. Yeah, that's trajectory. And update theta I as well. That's theta I plus some alpha I R tau I. So this is what you have collected in that trajectory, and then gradient of speed. So this is something we can compute, right? Or
Yeah,
can
yeah, because we know pi policy. What let's say we have let's say softmax policy, so we can take the derivative of softmax. So
right? But there
everything
is a small problem. The problem is that uh,
infinity.
yeah, infinity. So the trajectory is of infinite length. So for that, you can truncate the trajectory after a point when gamma raised to t is very small, negligible, becomes negligible. So you can play the trajectory up to that point and then stop it. Okay, so next form of policy gradient is follow. Just a second. So I'm not, I'm going to the, anyway, I have not given you the expression. Um, So what I was planning to uh, uh, stitch second, that will be changed out. And so the second expression is the following. So explaining what is this d rho pi theta. where this d rho theta d rho phi theta is defined as this number. So what does it mean? Means that what is the uh, so this is called discounted occupation measure. Occupation. So it. Okay, let's give an example. So say we fixed a state case and we have found the distribution of from the distribution of trajectory. But seeing the state is at 0, 0, 1, 2. So at 0, seeing the probability, seeing the state is uh, 0.1 probably, and say here it's 0.2, 0.15, 0.12, and 0.15, and 0.2, 0.2. So on. And gamma is okay. I'm not considering the gamma value. So what we are doing is multiplying this with gamma, multiplying this with gamma square, and this with gamma cube. And so on. So they're summing this all the probabilities weighted by gamma raised to t, and then normalizing it. So if we sum over all trajectories, this entire thing will be 1 by 1 minus gamma. So they are just normalizing it so that this becomes a probability measure. Okay, so now we'll prove this result. So V rho pi theta. So we'll show it for V pi theta rho is summation over rho is V pi theta is. So if we find the gradient expression for one is, if we find okay, so V pi theta is so we'll find only this expression for this. Okay, so I mean, from here you can go to uh, this v pi theta gradient of v pi theta rho very easily. So let's write this v pi theta. Sorry, this is not superscript. Let's write v pi theta in terms of q pi theta. So what will that be? Summation over pi a given pi theta a given s q pi theta is comma, right? So now let's expand this derivative. So this is sum and then multiplication, right? So we'll apply the rule of derivative. So in the first part, you will do the derivative of the pi theta, and in the second term, we do the derivative of the uh, other thing. So q pi theta. So now, first term, let's keep it as it is. The second term, we can write in terms of Bellman equation. Let's see what happens. So the first term, if you see, this expression this expression is quite similar to this, right? So if you have q pi theta SA, then gradient of log of pi theta is AX. So we are going towards something like that. So, okay, let us write the other way around. So q pi theta SA, gradient of pi theta is A given is. And the second term, uh, you can expand in terms of Bellman equation. But see that uh, first term in the Bellman equation, we expand q pi theta SA is RSA. Right? So RSA it doesn't depend on theta. So uh, that will be constant with respect to theta, and that will be zero. So it will be summation over pi theta A given as gradient. So only the second term gamma times is sum over S prime. P is A S prime. V pi S prime. So we can take this pi theta uh, a given is inside this summation or inside can you take or not?
Yeah, it is summed over. There is no S prime over there, so you can take it inside.
But it's a function of theta, right? Let me think. Okay, so okay, but yeah, so first we can what we can do is again I'm writing pi.
Actually, you're talking about putting it inside the gradient. We can't take it inside. Yeah, because it
Yeah,
is a function of theta.
we can do something. So okay, let us write this first term as let us write this as phi 0 is. So first term will be phi 0 s plus so gradient will be only for v theta, v pi theta spine. So it will be gamma times the s on s prime pi theta is equal to. So gradient of v pi theta s prime. So this, if you see, this is nothing but the probability that okay, I think I should write this summation in two parts. That will make it easier to understand. So first summation is over S prime, then second summation is over actions. So I'm keeping this thing out. I that will be something. Uh, then see, this thing is nothing but probability that is. So here is no action. Sorry, here is no notion of time here. So what should I write? Okay, so let us write S plus. S plus equals to S prime, given S equals to S. So this is capital S, a random variable. So current state is small s, and uh, next state is S prime. So the inner summation is nothing but this quantity under policy pi. So yeah, let us write that P naught S plus gamma times summation for S prime delta theta P pi theta S prime. So This is kind of similar as from where we have started. So this we have started with this, and now we have landed with a sort of recursive equation or something similar to the Bellman equation, but for the gradient. So if we do this recursion again, we'll see that we'll get this the following: P mod S plus S I P plus S. So here it will be just recursive thing. P not S prime plus gamma times summation over S double prime P. I should have write P pi theta because this is the probability measure induced by policy pi theta, but that's there. So S plus plus. So the next state is S prime, double prime, given S plus is S prime. Gradient of P pi theta is double prime. So if you continue doing this, then you'll see that we'll have the following. Summation over S P0 S times summation over equals to 0 to infinity. Probability that S. So again, I'm going to T anyway. So ST equals to S. It's sum it over S tilde. S tilde. S equals to S tilde. Given S not equals to S. So there will be gamma multiplied with gamma is to 2. See that there will be no expression left for V theta, gradient of V pi theta because of this discounting factor. As t tends to infinity, I mean, as we'll unfold these things, so gamma raised to t will be 0. So the last term will have no effect. So this is nothing but expectation. So this probability is, this is not probability. So expectation, no, still write it, expectation, sorry, summation. Still P not S tilde. This is 1 minus gamma times, sorry, 1 by 1 minus gamma times the d rho pi theta note or d note d pi, yeah, d pi theta of ST. So what is phi zero phi naught is tilde? That is, let's replace that. Phi naught S tilde is this. Okay. So instead of S tilde, we have S. Sorry, instead of S, we have S tilde. 1 minus gamma, let's keep outside. Then right. So we have got what we wanted. 1 minus gamma.
How did you get rid of that gradient? Uh, Gradient of
It,
E V.
yes, yes. Yeah, so that's what I was saying. So this is the second time I am getting that gradient unfolded, right? So what is the gamma factor multiplied with it? This is 1 gamma. Sorry. So
Okay,
this
you are
is
saying
the
limit
first
tends to
gamma.
infinity, it will disappear.
Yes, yes. Gamma raised to t will go to 0. So yeah.
Uh-huh. Okay, okay.
So this will be this expression will be expectation over S from the distribution d rho by theta, and then another expectation where A is taken with according to the policy by theta. Uh, and then inside that q by theta is A gradient. So that's what we wanted, right? So now why we derive this? We derive this because there is some resemblance with the actor critic we have discussed here. So for multi-binding, what we had is we had this expression, we had this mu a here. We couldn't we didn't know mu a. So what is policy gradient? Just replace this entire expectation with the immediate reward we are getting, or D. And what is actor critic like algorithm for multi-band? It is you estimate mu a, you replace the mu a estimate, sorry, the true mu a using the estimate of mu a, mu hat t. So the first expression we had was this expectation over trajectory. Now expectation we cannot compute. So if we remove expectation, then we'll have the just a reward of the trajectory. So this is equivalent to this is equivalent to RT is equivalent to small RT. Right. So if you have to anyway eliminate the expectation. So when you eliminate the expectation, the small this capital R of tau is equivalent to the instantaneous reward you are getting from pulling of the arm. But here, inside this, we are getting the expectation, getting the yes. This is equivalent to mu A, and hence, so we can replace this using an estimate of Q at phi theta. Yes. Okay, so I'm trying to bring more things on this. So now this Q, you know, and one way of computing this Q by theta. What is that? It's TD learning, right? So V by
Yeah.
theta or Q by theta, you can compute.
Yeah, 3D learning, yeah. Basically,
So
R plus gamma max of A, pi of, so take action A and behave optimally after that. 3D update.
yes, not optimally. So so
Sorry,
here
not
you
optimally,
have
according to
got
policy. According to
yes,
policy.
yes, yes. So we have this one fixed angle. So you know this function approximation for uh, TD learning, and you know function approximation for policy gradient. Uh, so what you do there is for actor critic algorithms. Input jumping some steps. Yes. So uh, what is actor? Uh, I mean, uh, if you have
Actor is
watched a
theta.
lecture, sorry,
Actor is theta.
okay, theta means the parameter, right?
Yeah, the parameter is the actor. I mean, kind of the action, right? So theta,
Yes.
the
So
actor is the
yes,
what is doing the action.
yes. So let's write the actor part. Actor is basically uh, parameterized policy class. It can be parameterized by some neural network policy class. Phi and phi theta such that theta belongs to some parameter space. And what is greeting?
critic is the current value
Yes.
of the
So
state value.
value, yeah, value found. You can uh, call it
Yeah,
parametric.
parametric value function, I guess. Yeah.
Yes, parametric value. So function. Yes. So that is if calligraphic if w belongs to some class. Now phi theta is phi theta is function from states to actions or uh, the uh, simplex of actions, probability spaces for actions, and MW is you initialize your uh, actor and critic with some uh, candidate function. So initialize actor with W0 and critic with uh, theta 0. So at this point of time, your policy is phi theta 0 and uh, the value function is f W0. So they have no relation at all. But why? But somehow we bring some relation. So for t equals to 0, 1, so on. What we do is we take an action. So we take an action according to the current policy. So what is current policy is which is pi theta 0, right? So in a way it's pi theta t. So at time t it is pi theta t. So sample action at from pi theta t given st. Then receive st plus 1 and r. Then we do two things. That is, first one is we update the value function. So that is exactly the what the TD update is WT plus 1 is WT as alpha. So there will be two step sizes. One is for the critic. So here I am updating the critic alpha t RT plus gamma if WT is T plus 1, if WT and then we update the actor also. So theta T plus 1 is, say there that step size is beta T. So this requires the reinforced update, right? So what did we do here? So pi 3. So here is one problem, I think, right? Do we have the Q function? Because our value estimate is only giving us the this v pi theta naught. That's what we are assuming. It's a function from states to actions. Okay, let's do some graph calculation somewhere else. So what will be the theta update if we uh, do not think about these things in terms of Q, theta T plus theta T, Q pi theta is T, AT, minus some baseline, gradient of log pi theta, theta T. Sorry, log of, can you, is this color visible? What's this little line?
Yeah, it is slightly lighter. Maybe anyway, you're gonna
Okay.
erase it. No, might keep it dark.
T, AT difference. So this is what we would have done if we knew on these things. But
Yeah,
we
this
don't
is the
know this.
reinforced algorithm, no? For matlab, this is sort of without the state thing.
Yes, yes. So uh, this is the reinforced algorithm, but
Matlab,
according
additionally, the
so
state information has come in.
no so
Before there was no state.
no so the reinforced algorithm is, I think, this algorithm, this where you use this estimate. Just a second. Have I written this? Yeah. Isn't this reinforced algorithm? Or maybe there could be many variants. So I don't know which version is taught in this.
So in the class, that actually the equation, no, that was so if you scroll down, yeah. So that was used like a static equation, and then that BT, no, BT was converted to a basically in a summation that is the summation over a state, and that was called the critic because that is so RT minus the critic because it is deciding whether the reward is good or bad. That is how this started in the class actually. So he used this the equation which you have written in the blue as the starting point
Uh,
to
actually,
start
no.
talking
So
about actor critic.
actually, here is it. and some ambiguity. So, okay, so critic is called this network which is generating the value function. That is some neural network which has weights W. Okay, so this is called critic. I mean,
True.
I'm calling it
True.
critic in this series. Yeah. Now, what you are saying
Is this
that
theta, this reinforce, so this theta,
yeah.
this
So
update, no, for reinforce is what basically R minus BT, summation over that. And
yes,
that
yes.
BT in the
I
reinforcement case was just a sum over all the rewards, right? And
yes,
when
yes.
you think of it, you add state to it, it is state-wise sum over the reward. And now, because it is the expectation over the reward from the state, it becomes your critic. And that's how he started the whole actor critic discussion in the class, actually.
Right.
So where
But
where the
got it,
actor
got
and the
it.
critic comes from.
So that thing I'll discuss in like I'll not take that particular baseline. I'll use something else, and yeah, that also you can interpret like similarly. We'll see. Yeah. Uh, but now when I'm talking about, I mean, taking the name critic, that means I'm meaning the neural network or the function approximator parameterized by W, which is giving us the value function estimate.
True, true. Got it.
So, okay. So now we have not written the actual actor update expression, but we are trying to find what can be written there. Q pi theta, theta t is ST AT. That is expectation of RT, that is the reward we get at time t, plus gamma times S A. Or okay, I'm taking the expectation, so there is no point of writing. B pi theta t is t plus minus. And for baseline, what is the criteria? What can be a baseline?
It doesn't have to depend. It should not depend on the action.
Please. So uh, does this quantity theta t ST, does it depend on the action AT? No, right?
No, it's the value, just steady state
Yeah.
values of states.
So what if I take that as BT? But I cannot take that as BT because I don't know that. So instead of that, what if I take this? So it's F WT test, which is the estimate of my V pi theta ST. Okay, so I have not yet solved, I mean, resolved this thing. And what if I take this RT plus gamma times F WT ST plus 1 as replacement of q pi theta st. So what does that mean? It means that, okay, so here there will be no BT. So we are not taking the expectation. So it's basically a sample, and V is estimated by FW. So now how the equation will look. Q is replaced by RT plus gamma. So did I do some mistake? Always no. Okay. F WT ST plus 1 minus BT, which is FWT ST, times gradient of log pi theta t AT next. So this is, I think, the correct update equation. I think it's true. Yeah. Now, so these two update equation are similar. One is multiplied with the gradient of the log of pi theta at given st, and another is just similar. Now, people have tried different type of things. So this, if you see, is you're updating the parameters in every time step, but it may not make much sense to update it in every time step. So we'll have tried like to try a policy for some time to keep on updating the maybe the value that means the critic, but to keep your policy fixed. So that kind of approaches has been taken, and yeah, that's basically the algorithm of active video. Okay, I think I have missed 1 minus gamma here, right? So there is one. Yeah, there is 1 here. It's 1 minus gamma. It's, I think, now it's correct. So there is not much time left. I'll now go to the previous lecture where I was stuck, and there basically I have to go back to multivariable calculus and resolve that thing. So where I will start is at finding gradient of E theta, and theta. So that is nothing but gradient of uh, E pi, D pi. Yes, theta as gradient of. Am I audible?
Yeah, yeah.
Oh, I think there is some connection issues. Okay, so these are scalars, but this can be written as delta phi sum over uh, v pi this thing is can be written as sum over so they say that the state space is of continuity n. So phi pi I d pi I. So it's the ith diagonal element times f pi theta plus similarly this is gradient of number I. I think there will be half there and one minus here. Yeah. So d pi I if I theta square. So the gradient will then be so here mu pi is from this state. So the gradient will be gradient of this one. This is only depending on the theta and some amount of half will go away because of this two factor. So if you see this of a scalar, if you compute gradient of say scalar function, I'm not writing AF, something else, G, G theta. This will be delta G theta and delta theta 1, delta G theta, delta theta 2, and so on. So say now yeah, theta is dimension 2. So let us replace here this by a phi theta. So G theta replaced by if I theta square. So this will be 2 if I theta then delta of I theta 1 and similarly to theta theta 2. So let's keep this thing in mind and use this. So this will be d pi I into if I theta times gradient of a phi theta. So this is a vector. Whatever multiplied with it is a scalar. Same here and same here. So can we write this scalar as a okay, let's not go there. Fine. So this is the gradient, and let's see what we have done for the linear case. So we have computed the gradient, and this is our equation. Let's just copy as it is from here. What will that look like? In minus beta t summation I equals to n v by I by. So now I have forgot where I'm writing the superscript by or others. Okay, so let's write superscript v by. So what is I here in this summation? I is state, right? So this is for gradient descent. So what will be the SGT update? I will be replaced by ST. SGT update. theta n plus 1. So we beta n time minus n minus d pi is. So d pi is also from a distribution, so that will also go away. S n plus if st theta is gradient of f theta. Sorry, I missed. And okay, let's write this in a better way. If st theta minus v pi fn. So now we use the TD idea. TD. Okay. What was the TD idea? That is replacing V by Sn by one step update. That is R, the current reward, plus gamma times V if St plus 1 given theta. So this is not theta, theta n. It's 1 theta n minus minus. So let's write this as plus R n plus gamma St plus 1. So do you think there should be some change? Or yeah, right. So instead of this, should also have this, isn't it? That's what we have. So this is all. This is all I had for today's tutorial.
Can you
So,
scroll up to that equation just once before we close?
which equation?
We should just change, yeah, in the actor.
Yeah.
Yeah, in the actor. Okay. Okay, I think in the class what they did, no, the second term, no, gradient of FWT over W, and that gradient of pi over theta, it proved that if those are equal, then these are uh, the the 3D update. Sorry, that what do you say?
The
The updates to the theta parameters and W parameters are exact same equation. For he assumed that alpha, probably he didn't take care of that alpha beta. Given you take alpha as the same, then they are the exact same update, is what he proved, I think, in the class. I'm also like, I fully not understood. I have to go revise, but now it makes sense that when you write it in a algorithmic form where you can code it, he didn't approach it like programming it. He approached it like from a conceptual point of view, and in that, in the end, he proved that the gradient of f, if the gradient of f equal to gradient of log, then the TD of the two updates are the same.
okay.
Yeah. And
But
then,
how?
but the only thing is, the theta is only, so let's say you have a parameterized space where for every action you have a theta. You only update theta for that particular action, and you update uh, the state irrespective of the action. So the theta node, if you have like if you have, let's say, you choose, let's say you are implementing it in a form of neural network, and each uh, uh, this thing, each action has its own parameter set, theta. So theta A kind of thing. You know? So you only update that for the action you took and not any other action. That is the only difference, but the term is exactly the same you are saying. The two updates are same, which is he started from a very conceptual kind of point of view,
Okay.
which was I didn't understand much. I'll be honest with you, but at least before this lecture, I was thinking of it as uh, these updates, well, the update to the states as well as the update to the policy are exactly equal. If you remove
Yeah.
those, if the terms are equal, like the gradient terms are equal, and maybe I have to go through it again after listening to your lecture, but this is the algorithmic perspective on it. He didn't really explicitly write down the uh, like
Yeah.
this
Got
algorithmic
it.
form.
Oh, got
He was doing it from a theorem kind of point of view.
it.
That's why it was really hard to follow. But this is a more algorithmic, and it makes sense that there should be a gradient term. But in the end, he uses that proof where he proves that if the first term is equal, the gradient of W is gradient equal to gradient of theta, then the two updates are the same.
Okay.
That's what he proved in the class, which makes sense now.
Okay. Nice. So unknowingly, I have took a different route and same came out same.
Yeah,
Yes.
it's pretty cool. Yeah. So thank you so much. You have a nice weekend.
Yeah. Yeah. Thank you. Okay. Okay. So here I am ending this lecture.